Yeah, I go to MATLAB. So I use called System Identification Toolbox. So before the name is called IDENT. Can you see this? What I'm typing?
Yeah, we can see.
Yeah. Okay. So have you ever someone use this toolbox? Like this one is modeling, just with the first project. For example, we import data. Import data because this one I already give you the data. There's lots of people. The name here, I list here. This I select one of the person. He did the exercise, did the experiment, and then I read the data, and then I build the input and output, and if I run it, so I have the input output already, right? But I don't want to. You can also use the programming to continue to do this, but because this subject is not mainly for modeling, it's just like one project use modeling. So I ask you to use identification toolbox. So this identification toolbox, if you type IDENT, and then this one will appear. So in that case, you need to import data. So the data you need to import. So you import actually you can from different uh, uh, domain. So you can use this is time domain data because we our input output is time domain data, and also we can use frequency domain data. Frequency domain data, I'm not sure you heard about this frequency analysis. You use different sinusoid with different frequency, and then you can got some point, and then you can use frequency domain data. But here I use the most popular one, time domain data, and then they ask what's the input. So input I already uh, developed this U, but this they need a vector, so I use U transpose because my U here, if I U here, if I says, so my input is a is a is a is a raw vector. So raw vector is not a column vector. We need to use column vector here. So I put a dash here. So and then I have y is called y what's the name, ycp. So it's ycp is the one is output. So you need to have input output. You just simply input the input output because I already give you the time data, and then you need to find starting point. Maybe starting time we start at 0, and then sampling time. All sampling time is 2 seconds, so I put 2 seconds. Uh, because the sampling time, because for the breath signal, uh, if you want to do breath analysis, breath by breath analysis, you normally at least 2 seconds you have one breath. Uh, so that's why your sampling time cannot be too fast. But I import this data. So this data imported here. This data imported, you can see here. And then I analyze here. So in that case, I do it slowly, and then you can see the powerful modeling method. So first uh, we can show the data, what the data looks like. So this we inputted the data. Actually, we do the data looks not that bad, right? Still have some noise, but it's something like this, right? But we are only for example, we are only interested with on-site part. If we do modeling for on-site, we need to select on-site part. So how to do that? They have pre-processing. So pre-processing is the one we already learned, signal processing. So for example, they have lots of methods. So they can select channel, they can select experiments, they can merge experiment, they can also select range. So we can select range first, and then we can remove mean. Sometimes the mean is not useful, and remove trends. And we can also filtering. So filtering, for example, here I make a selection filter. So this is the frequency called FFT. They do frequency. And then if you see this part, high frequency noise, you want to get rid of, it's very simple. You just like define. You only need this part. Maybe this part. This part. Small part. And then I do filter. So this is a filtered signal. This is the one. So this is very quick, right? You do filtering. So you can see the filter, they change the low pass. This is like a low pass. You don't need to know what they have done, but they already done for you. So you filtered. So in that case, you can see in the low frequency they not change too much, but in the high frequency they become lower. So in that case, we insert this signal. So this is the filtered signal. We look at the filtered signal. So you can see this filtered signal is smooth, right? Uh, it's quite smooth, right? But they make some because for input you use filter, it's not good. So my suggestion is you only do filtering for separately. For the you can do you before you into this toolbox, you can do filter yourself and then put here. If you use their toolbox, they will do their filtering. So filtering, you can see, I believe this filter is over second order. So this have a overshoot. So this is not very good. So for this one, but but we still can continue. For example, if we want to analyze this one, we put this signal to the working data. So this means we already forget, the blue one. We only look at the green one. And then we start to do pre-processing again. You can do pre-processing. What we want to select the range. So we don't want to, we only want to this range. So the onset of exercise. For example, as we select here, right? Select here, and then we insert. So this one is only half of this signal, and then we put here to do analysis. So this one, if we draw the figure, so we only select the first step, this one, and then we can start to modeling. Modeling is this input output we already know, and then the next step is we based on input output we find the best fitted model. So this something like least square method, but it's more complex. So we look at, for example, we have lots of model, right? We have state space model I discussed before, right? When you use the Kalman filter, you use a state space model, but we normally transfunction model, the one we are familiar is transfunction model. So you can select what's the order. So number of pores is the order. So we select first order. So first order, and then we also select uh, number. They want to ask a number of zeros. We maybe select zero. We no need zero. That means normal first order. So this one you can select continuous or discrete time. For example, we select continuous, and then we estimate. Simply push the button. They start to do modeling for us. So this one you get the model already. So we can see the modeling result. You can see it's not quite good. So if you use first order, so this one is not quite good. So you need to tune this model. Maybe we select. The main problem is we didn't get rid of mean. So maybe we need to pre-process again. We remove mean, and then we do the modeling again. And we do modeling again. Transfer model. Transfer. We still, for example, the 0, and we estimate. Probably better, but then cannot guarantee. Slightly better, but still have some problem because of we use high order, for example, third order. Third order is already unstable, so so this one is not good. So put in the rubbish bin. It's not good. So actually we can. So this part we didn't select the best model yet. So we need maybe we still need to do pre-processing. We maybe remove the trend as well. Remove the trend, and then we after remove trend we do the another time estimation transfer function. We use first order. It's a little bit better. I think if we do so, this one maybe have some problem. So this model is not good. We select different. I think it's because of input have been damaged. So this is I just teach you how to use this method. But the best way is like you do pre-processing first and then input to use this toolbox. They have input and output better. You can see now currently the input output is changed to totally different shape. So because of the pre-process they are doing is too much. I think we didn't do good analysis. And if we recover the original data, and the original data, if we do the no pre-processing, we maybe just uh, remove the maybe we just remove the trend the mean values, maybe will be better. So we do the estimation. So first off, so this time is better, right? So the modeling is much better. So you can see after the modeling, your system is very smooth. There's no noise. So this is modeling based filtering as well. You can thinking about like this way, and then you also want to know what's the time constant, what's the statistic gain. So this is the model information here. They tell you. So you can see your time constant is quite long. So for this one, it's a you need to make this as one, and then this one you can find the time constant. So this is for input. For the onset, you can also do offset, but this is both input inside and offset. So this is onset and offset. So this is the toolbox. You use this toolbox, you can get the model and do analysis. So this is quite a powerful toolbox. I not see no, I not save this one. So if you select the first project and also some other project related with dynamic modeling, you just use the system and ident. So I show you like, but in the future, this called IDENT, this system identification toolbox. In the future, this name will be changed. So they will use system identification. I'm not sure now it's okay. System identification. If I use this one, they also okay. So now in the future they will just use system identification. Maybe they change the name. I'm not sure if you use 2020. Maybe you need to use system identification. Yeah. So we not see. So this is for today's lecture. Today's lecture we also have another thing. This is the system identification toolbox, and also we have that's when doing exercise. That's a long time ago. Maybe we want to build a model. This one is something we this is accelerometer signal, and then this is the one doing different. This is we also record ECG, and then we build the relationship between working speed and also uh, and heart rate and working speed and heart rate. So we have developed. We found that this is not linear, but we use different speed. At different speed, the time constant is different. So human is very adaptive. So we have developed some. This one is just use the technique I showed you. We build the model and to do the statistics, and we find the nonlinear relationship between your speed and the time constant. For example, you can find at 3 kilometers per hour, what's the time constant? If you and also from if you jump another big jump, for example, from 3 to 10, this big jump, and then your time constant will not like linear system. It's a it's a constant time. It's a the time constant is not changed, but actually we find like if you small jump, your system will responds very quick. Your time constant is very small. But if you use a very big jump, your will be take longer. So this is a human. Actually, it's not a machine. So we this one finding. Uh, this another one, another paper I put is this one. So this one is a paper published in the physiology management. So this so you know like you maybe currently the physiological signal you are thinking about is ECG, EEG, EMG, and also breathe, blood pressure, and something like that. Actually, just the respiratory, cardiorespiratory signal, there's lots of different measurement. So there's lots of like even cardiac output. So I show you this one. This one is mainly I use static modeling. So I two paper. One is dynamic model, and the second one is a static model. The static model is we use support vector machine. Actually, it's a kind of machine learning modeling method. We will discuss next week. Discuss use support vector machine to do classification, and the classification actually is you can treat it as a special case of regression or uh, modeling. That means for modeling, the output input is continuous, but for classification, the output is discrete time. For example, sometimes it's only 0, 1. If you want to classify patient or healthy people, you only have 0 is healthy, 1 is a patient. So you need to only, I mean, discretize the output. So this is the one we discussed. This you can see lots of signal. We at that time we estimated. We want to find the relationship. So here I can see this. This is a VO2 and calculate VO2. These are also other signal. So this is a support vector machine. It's quite complex. Maybe you no need to understand. Just like support vector machine is also MATLAB. I will show you next week. They have MATLAB also have toolbox to directly use, and you just need to explain them as well. Just like this is the guy who will do the exercise. They have measured lots of things. Actually, K4B2 uh, measured most of the signal, but some signal they cannot measure. For example, this is called cardi output. So they use Doppler radar to, for example, if you want to know athlete is very strong, and then you just want to know what's the stroke volume. If your heart is very strong, your one stroke is equivalent with other people's two stroke, and then you are very strong. And this is we can directly measure. This is directly measure. Directly measure, of course, is very difficult, and you need to a very expensive machine, and also the people will be very uncomfortable. They put very hard things to put on the under the neck, and then they measure, and uh, and then they use ultrasound to see this. And based on this, this also not direct measure. If you want to golden standard, you need to use invasive measurement. You put some, you inject some chemical things, and then you can and measure the uh, blood density of this material, and to see how long this material is go the whole body of, and then that we can estimate your cardiac output. So your how strong is your heart, how big is your heart, and then but this paper is mainly we use some heart rate or some other easily measured signal to estimate somebody's uh, stroke volume. Stroke volume. So this is this paper. So there's lots of signal we are interested in. We can use this is a nonlinear. This is a nonlinear regression. So it's nonlinear relationship. You can see this one is a linear relationship. Before the prefer, before the statistic, they all want to transfer this one to a linear. For example, if this is nonlinear, they maybe take log or take some transformation. They put as linear and then they do modeling. But now they can still directly use nonlinear modeling method. So that's why I just give you some hint, but not go detail. So this is this lecture I prepared. Uh, but next lecture we will discuss classification. So this is modular 3. We go to so classification is very important for your next stage. So yes, I think the rest, I mean not cannot see the rest. Another at least 3 or 4 project is related with classification, because after you do signal processing, now you are very capable to do signal processing. You can find all the features. For example, you can use DWT for different level DWT approximation and details as a feature, and then do classification. And so that's why classification is very important. Next week I will discuss classification. So first is K-mean. K-mean is called unsupervised classification or unsupervised learning. So it means like you have two you have give you data, but will not tell you what's the label. For example, which one is a patient, which non-patient thing, and then you need to uh, see how close. You maybe see two class. This class is close together, another class close together, and then you find, oh, this is a two class, and then you can automatically use k-mean to separate. Another is SVM, which is support vector machine. I use regression, but this one you classify. So you have two point. One is dog, another is cat. Can you find this is a uh, Hilper plan? You can find a Hilper plan separate these two kind of uh, animal, and then this is called classification. But we discuss, you find the best boundary, the biggest maximum the boundary. And also when I will teach you how to use MATLAB. They have the MATLAB classification learner. This one you need to know how to use it. So just like the one I teach you how to use identification toolbox, they are very similar. Just like you just follow the rule. Actually, this one they all have video. You can use that one to